such as things about buildings, which buildings are commercial versus residential. And that's sort of just the tip of the iceberg of things that you can think about with satellite imagery. So our company started in 2013. It's been a pretty exciting journey so far. And the reason why it started, and the question was like, why now? Why do geospatial analytics? So there's a few different areas that make sense as to why this makes sense to do now. One of the first ones is the commercialization of space. So companies like SpaceX are making things a lot cheaper to send into space. There's a lot of companies that have leveraged that and sent more satellites into space. More satellites taking more images gives you huge volumes of data. With all this data, if you want to analyze it at scale, you definitely need a large amount of compute. And then also in this field, while you guys are here today, there's a lot going on with machine learning, in particular deep learning. So this is around 2013, and these different areas are having their own sort of proliferation. And at the crux of this, there's a need for geospatial analytics, a company like Orbital Insight. Another thing to note here is that none of these things are particularly new. For instance, satellites have been up and taking pictures for decades. And we all know that neural networks have been around since the 80s. But now, with all of them together and all their respective proliferation, we get a lot more that can be done. So, Orbital Insight, we don't actually do any of the launching of satellites. That's the hardware. We are a software company. And we focus on working with tons of different types of data. We have this huge funnel of different data sources. Things like geospatial data in the form of imagery, from aerial imagery, from satellite imagery. And there's an engineering challenge to just analyzing that at scale, making sure we can get all this data into our system and run it at scale and create meaningful solutions for customers. Today I'll be talking more about the machine learning computer vision piece, where we analyze some of that data. And it's not always just about a given snapshot. It's not just about, here's an image, what's going on in this image, but almost always we're looking at the trends over time. How are things changing? How is the world being affected by different things? And then on the customer side, we have many different ways to deliver to different customers. Because there's different customers that want to analyze the different aspects of what's going on. Some customers care about things like, oh, I just want to monitor this building, maybe this factory. There's other customers that want to look more at something like a citywide scale, maybe a statewide scale. And then others that want to know things about the entire country or the entire world. So a little bit about machine learning at Orbital Insight. The first thing to note is that the data that we work with comes in a lot of different variety. So this is just the imagery. And things to note here, in the first three panels up here, you have optical imagery in the form of RGB. And there's different providers with different characteristics, and those characteristics usually have a trade-off between, if you want fine-grained detail of things like buildings and vehicles within a city, then you have to zoom in and you don't get to cover as much of the land region. Whereas if you do want to cover more land, you're going to take potentially a hit in resolution. And so at Orbital Insight, we want to leverage all the data that we can. So we have to build things that can use all these different data sources and take advantage of the information that comes from both or from different scales. The fourth panel here shows the fact that not all of our imagery is optical. So some of the imagery, we actually get different channels, like things like infrared. And this isn't necessarily a difficult thing on its own. Like for machine learning or for neural networks, just to work with like a different channel of data isn't that difficult. But when we're working with all these different data and we want to combine things and we maybe want to learn stuff from one task and apply it to another, that's where it can get a little challenging. And the last panel here, this is fun. So this isn't even optical imagery. This is an image of radar. And I'm showing it as an animation for two reasons. One is, if you haven't seen this type of data before, it's kind of difficult to understand what's going on. So showing the animation, you can actually see that there's objects moving in and out. This is a port where those are ships moving in and out. And it also highlights the fact that it's not just looking at one image, but it's looking at the sequence over time. And how can we build machine learning models which take account of the temporal domain, not just for the radar imagery, but for all imagery. And so that's what we've done at Orbital Insight. And here I'm showing just a fraction of the models and different tasks that we've actually worked on. A lot of them revolve around things like generic tasks like object detection, where sometimes we can characterize an object just with a center point. Other times, if either our needs or our customers' need to actually know things about scale, we can characterize them as bounding boxes. And then in some cases, we want to give the full outline, the segmentation maps or the polygon of the objects. Beyond object detection, we have algorithms for image classification, for semantic segmentation, and sometimes we even have nuanced tasks that are sort of niche in terms of like here where we're measuring tank shadows, where we're actually trying to look for the volume of oil in these tanks based on where the roof is if it goes up and down, where we're looking for things like circles and shadows. Okay, this is a fun question. It's something that I've gotten a lot over the years in terms of being a deep learning practitioner. Maybe many of you have had it as well. And it goes something to the effect of, hey, what is your network architecture? What are you using? And it's definitely a fun question. And I'll explain today why I really don't think it's necessarily the most fruitful question to ask. But that being said, let's have fun with it today. So things like, if you're doing image classification, people often go to ResNet, Inception, AlexNet, et cetera, BGG. For things like object detection, you have Yellow SSD, FastRCNN, FastRCNN. And then for semantic segmentation, this is a popular network on the left, which is the UNet architecture. And so what I want to highlight here is a few things that there's a lot of popular architectures that other people in the community have found to be effective. However, there's also, you usually see the best architectures. There's so much search going on with architectures, and sometimes people get just a little bit better accuracy. But is that really because the architecture did something, or was it kind of luck, maybe a little bit of both? This image on the right captures something pretty well. This is from the DeepLab v3 paper. And so this talks about, we've basically learned that there's good ways to approach deep learning where you want to incorporate multiple scale. Maybe you want to add skip connections because you can pass information forward or propagate information backward. And so there's a bunch of different ways to do it with downsampling, upsampling. You can also use dilated convolutions. And this is like a fun thing that people talk about. And even in Orbital Insight, we have done our own network architecture search. It's been fun. We've had our fun with naming architectures. Like even in academia, you see these fun different network names. So there's, like in this case, UNet. We've also seen VNet. We've seen UNet++, WNet. There's TiramisuNet, which is a UNet that has these dense net blocks as the subblocks. So anyway, it's a fun game, but really, it is definitely slightly important for us in terms of, because we're working with so many different tasks, we can't just be blind about the network that we choose. And we need to be careful about if we're looking for things like small objects to make sure that we don't have too much downsampling, or if we need more context, we need to think about how to use networks that have more receptive field. But I really think it's a little bit of a distracting question, because if you just focus on what the network architecture is, you're kind of learning, you're ignoring some of the other important facts. So really, a better question in my mind is something to the effect of, what are your machine learning keys to success? And so at Orbital Insight, some of these topics have really been the make or break for certain problems. So same question to other people, what makes your task work that if you didn't have that piece in your training or your pipeline, that it wouldn't be as successful? So for us, things like augmentation and sampling are huge. And they're also interesting because you can't just do what everyone else is doing in terms of, for us, we're working with satellite imagery where people are allowed to build and move, and nature is allowed to grow in its own way, irrespective of where the camera is in the sky and aligning with the camera axis. So we're actually able to, in most cases, rotate our images 360 degrees and flip them. This is probably not something you'd want to do in different domains. For instance, if you're focusing on self-driving cars, hopefully you don't have to train for the case where the camera's upside down. That's probably a bad case. Other things that have really helped us are things like how do you enforce regularization, things like loss functions. And so these are important in the sense of it's not just about one benchmark that you're trying to achieve or just using one loss function. Oftentimes for us, since we have so many different tasks, sometimes there's different loss functions that you can enforce some things that you want to keep consistent. For instance, for us, if we're working in the temporal domain, how can we incorporate some of that information into the loss function itself or another part of the training? And the image over here, sampling's big because let's say you want to do something like us, we want to do everything where it works at a global scale. And so if we have algorithms for building detection, if we want to collect a data set and we just randomly sample images from anywhere in the world, well, most of the regions aren't going to have any buildings. So you need to be careful about how you actually build the data set. And also when you're training and you're creating mini batches to make sure that you're sort of enforcing the network to do well, as opposed to just saying, oh, there's no buildings and I'm doing well on my current data set. So now I want to switch gears and talk about a few applications that we've built. The first is around consumer traffic. This animation shows what some of the data is that we actually work with. This is some of the highest resolution imagery commercially available. And you can see variability in things like lighting, there's seasonality effects, you can see snow in one of the images. And in this case, the cars are just a tiny little object. One of the first machine learning models that Orbital Insight trained was around car detection. And so why did we do that? Or how is it interesting? Or who can it be useful for? So we built an algorithm to detect cars in parking lots, these tiny little objects. And if you link that up with knowing where different stores are around the world, you can get information of how people are shopping and the trends of things like how are they shopping at Walmart versus Home Depot. And you can do this at scale for, right now we track hundreds of different retailers and hundreds of thousands of different stores across the US, and you can see these large-scale trends. And so in this case, here we're showing the Orbital Insight look at the trend of the car count, which starts off high for Macy's and then goes down, stays flat, and goes down. And you can see a similar trend from the Wall Street consensus. However, because we're analyzing images that we get today, the trends lag the Orbital Insight data by just a few months. So this is sort of a bonus slide in the sense of we built an algorithm to count cars, and it was intended to look at things like retail traffic, but we can use that for many different cases. So in one use case, we just counted the cars on major roads in the US and showed how it correlates with US gasoline demand. And then on the other panel, the animation, this is looking at a city, this is Nanjing in China, and just from counting cars, you can see patterns of how the city is growing, of how suburbs around the city are popping up. And this is just from counting cars. So even though now we have more algorithms that can detect roads, can detect buildings, look at how those are changing, there's still a lot of signal just from one model. So switching over now to talk about some of the roads and buildings and infrastructure monitoring that we do. So some customers want to know pretty large-scale trends of things like where are the roads, where are the buildings, how do they connect, how are they growing, how are they changing over time. And so this is a static image showing one of our models on the results on one model. And again, we have the temporal component where now you can actually see construction happening. You can see roads being built and these individual houses popping up and how our algorithm can handle detecting all those different things. And so this is great for this scale of imagery, but sometimes customers may also want more fine-grained information. So in terms of building detection, maybe they don't just want to know roughly like where are buildings being built and how many or what's the area, but they want to know fine-grained detail about, tell me like the individual counts of buildings or give me the actual outlines of the building footprints. And so here in this case, we actually have to train models to do instance segmentation, which gives you the boundaries of the buildings and makes sure that neighboring buildings are recognized as separate buildings. And again, in this case, we have the temporal domain. So this is looking at new housing construction in the US. And so we can do this at scale where we're looking at different neighborhoods and how buildings, the inventory of buildings is changing over time. So the last application I want to talk to you about today is around detecting deforestation. This has been a really great project to work on. It's been fun to learn about the space, and today I'll give you a chance to learn a little bit about it as well. So if you look in the news, these are two different articles that actually came out in the past 2 months. And they seem pretty contradicting, right? So what's going on here? Part of me kind of wishes this was like a fun math class to teach you about, if you've heard of Simpson's paradox, where depending on how you look at the data, you could have multiple downtrends actually seem like an uptrend. But it's more just about really what's going on here is the fact that researchers and journalists and policymakers don't always have the best data at their disposal. And so how can companies like Orbital Insight help? So honestly, these articles do a great job of describing what's going on, and they're not trying to contradict each other or be flashy in any way. But let's learn a little bit about what's going on. So when you think of forests, maybe you just have one picture in your mind about what those trees look like, what they correspond to. But honestly, there's so many different types of trees around the world, and there's so many different types of forests. This is just one classification that we'll talk about today, but it is not the be-all, end-all of forest types and classifications. So this image shows a natural and a planted plantation forest. On the top is the natural forest, the rainforest, which has these clumpy, randomly grown things that you would see in nature. And on the bottom is the plantation forest. In this case, it's palm oil. And you can see the trees that are grown in these nice, neat rows. And it's not as random. And so when you think about the data at disposal, if you say these are both forests, you're not necessarily wrong. However, their intents and purposes are vastly different in the sense of the natural rainforest is natural, and the plantation forest is more like a crop. It's actually grown with the intent to eventually be cut down. So when you do things like detect deforestation, if you say this forest was cut down, well, yeah, sometimes it was actually planned. And this isn't necessarily a bad thing. I mean, there's plantation forests for things like timber, which allows us to build homes and furniture. So if you look at data, which you might get from what people looked at in the articles of, this is looking at Malaysia as a country and just looking at forest cover. You'll see this bright green map which says, oh yeah, the entire country is mostly covered in forest. And if that's all the data that you have to work with, it can be a little challenging in terms of what do you do with that data, or how do you dive deeper. So what we've built using deep learning is a classifier which can recognize many different types of lands, but in particular, it can recognize the difference between planted forest versus natural forest. And this is the image I showed earlier, which is a high-resolution image, which, as we talked about earlier, if you have high-resolution images, you get fine-grained detail, but you only see a zoomed-in portion. And I think as a practitioner, if I showed this to someone and said, hey, look, deep learning was able to tell these two different forests, people would say, yeah, obviously, like there's a huge texture difference between these two forests, maybe even a little bit of a color difference. Like deep learning should nail this. However, this isn't actually the imagery that we ran it on. I'm showing it here so that you guys can understand the problem, but I'll show in a few slides what the imagery actually looks like, and it's the wider area, a little blurrier. And so our algorithms were able to still learn that there's some sort of texture difference, and even in the lower resolution imagery, and able to pick out natural versus planted forest. So this is great. We can do it on a small little image that I just showed you. We can also do this at a very large scale. And so now if you look at a country like Malaysia, it is true that there's a lot of forest, but now you can actually start to see the different areas of natural forest versus plantation forest. And this data is super useful to researchers, policymakers, and journalists. The other thing to note here is that in terms of scalability, we're able to run this at a pretty large scale. We've run it for many different other countries around the world where there are palm oil plantations, and we see similar results. So the image I showed earlier from previous research, where you only just saw forest, there is some data out there about plantation forests, but it's a little more expensive to collect. Either it requires a manual process, or you can't do it as frequently because the updates are too slow or not scalable. So now with Orbital Insight, we're able to do this sort of with a click of a button, automated. And if we compare that to the previous results, you'll see that now you get more fine-grained detail, more information. And what's great is that this data is detailed at many different zoom levels, in the sense that you can look at the entire country, and if people want to ask questions or get answers about what's going on at a country scale, they can get that, as well as if there are others who want to zoom in and look at other different land use types of what's going on. This data is, all that data is there, and we can run this at a global scale. And then again, the last piece is the temporal component of what do we do in terms of looking at things changing. So this is actually the imagery where we are running the algorithms. And so it's a little harder to see, at least on the far left, where there's the natural rainforest. In the sense of, this is one of the more obvious examples where a huge area got cleared, which was a natural forest, and then it looks like it's becoming a palm oil plantation land, but the trees aren't necessarily grown in. So we're able to detect large changes, which is good, but we're also able to detect smaller changes of just a small patch of forest is being cut down. And this is also very useful and informative to those stakeholders I talked about earlier, researchers, journalists, in the sense of, it's not just about where are trees being cut down. So one of the first answers is, what types of trees or forests are being cut down? Like, there's a big difference between if it's a palm oil plantation that was sort of intended to be cut down versus a natural rainforest that's cut down. But also, the real question is, why are things being cut down? In the sense of, was it cut down so that people can build homes there? Was it cut down so that animals can graze there, or to build more palm oil plantations? And now, because we can look at the change over time, we can start to answer a lot of those questions. I want to leave you today with a quote from our CEO and founder, James Crawford, in the sense of, we've built a lot of applications. What you've seen today is only a fraction of what we've built today, and an even smaller portion of what we want to build in the future. It's been a really great journey to be able to answer some questions for customers that weren't necessarily possible at the scale today, but there are even harder questions that we want to answer in the future, and even harder applications that us as a company need to build around such that we can answer those difficult questions. Thanks for listening to me.